Welcome at the Kistler webinar for signal processing. In this webinar, we are going to cover the topic filters. My name is Pascal Wolzhauser and I'm product manager for the handheld platform. Why are we using filters in signal processing? Mainly we are using filters to sort out content that is not of interest and or could cause undesired or disturbing effects in a later stage. For instance, if you have a signal with a noise signal superimposed to it, you can use a filter to get rid of this noise. By carefully selecting filters, we can improve the signal-to-noise ratio significantly. In signal processing, frequency content is always subject to filter. Therefore, filters are always characterized in the frequency spectrum. Important terms we are going to explain during this webinar are filter types, cutoff frequency, filter order, frequency and phase response, and filter characteristics. In signal processing, we mainly distinguish between four filter types, which are low pass, high pass, band stop, and band pass. Where the last two, the band stop and the band pass filters, are a combination of a low pass and a high pass filter. If we have a look at the frequency responses of the different filters, we can see for the low pass that low frequency content is passed through the filter and high frequency content is filtered. If we have a look at the high pass, we clearly see that high frequency content is passed through the filter and low frequency content is filtered. When we have a look at the frequency response of the band stop, we clearly see that it's a combination of a low pass and a high pass, which means low frequency content is passed through this filter as well as high frequency content is passed through this filter. However, there is a frequency band in the middle which is filtered. If we have a look at the band pass, which is basically the opposite of the band stop, again we see that it's a combination of a low pass and a high pass filter. However, in this case, low frequency content is filtered and high frequency content is filtered, and only a defined frequency band in between is passed through the filter. When we are talking about filters, an important term is the cutoff frequency. The cutoff frequency is the frequency when a signal is damped by 3 dB or amplified by -3 dB. An amplification of -3 dB equals a reduction of the input amplitude of the signal to around 71%. In the graph below, you see an example of a frequency response of a first-order low-pass filter with a cutoff frequency of 10 kHz. In the diagram, you see a red marker with the -3 dB line, and the -3 dB line crosses the blue frequency response at 10 kHz. So that means the -3 dB point for this filter is at 10 kHz, and this equals the cutoff frequency of this filter. The filter order describes the roll-off characteristic of a filter frequency response above the cutoff frequency. Important to know is that an N-order filter has a roll-off of N times 20 dB per decade, where a decade is a multiplication by factor 10. For example, from 1 kHz to 10 kHz, we are talking about a decade. if we have a look at the frequency response diagram, we see three different lines. A blue line for a first order low pass, a red line for a second order low pass filter, and a green line for a fourth order low pass filter. Now, if we have a look at the blue line, since this is a first order low pass filter, we would expect a roll-off characteristic of 1 times 20 dB per decade. If we have a look at the frequency point 100 kHz, we are at an amplification of minus 20 dB. 1 decade above, at 1 MHz, we are at an amplification of minus 40 dB. So this means the amplification is decreasing by minus 20 dB, which equals a roll-off characteristic of a first order low pass filter. If we have a look at the red curve, the second order low pass filter, again we check the 100 kHz point, which is at minus 40 dB, and then 1 decade above at 1 MHz we are at minus 80 dB. So again here, since this is a second order low pass filter, we expect a roll-off characteristic of 2 times 20 dB per decade, which equals minus 40 dB, and this is the case for the red line. When cascading filters, we have to know that for the roll-off characteristic of the overall filter, we can sum up the orders of the cascaded filters. So as an example, if you are cascading 2 first order low pass filters, we end up with a second order low pass filter. How can a filter be implemented in the analog world? In this case, I'm going to show you how you can implement an RC low pass filter. First of all, we are going to have a look at the simple voltage divider. The voltage divider consists of 2 resistors, R1 and R2, an input voltage U in and an output voltage U out. Important to know is that the voltages are always proportional to the resistors. So U in is proportional to resistor R1 and R2, and U out is proportional to resistor R2. Since the resistors R1 and R2 are frequency independent, the output voltage U out is not changing when I'm changing the frequency of the input voltage U in. So but if I want to build a filter, I somehow need to be able to make the output voltage frequency dependent. So how can I do this? I can do this by replacing resistor R2 with a capacitor C1. The resistance of this capacitor is defined as Xc, so-called reactance. The reactance of this capacitor is 1 divided by 2 times P times the frequency times the capacitance. And as you can see from the formula, the reactance or the resistance of this capacitor is frequency dependent. So that means when I'm increasing the frequency, the reactance of the capacitor is decreasing. Since the output voltage is still proportional to this resistance of the capacitor, this means also that the output voltage is changing with my frequency. So now when I'm changing the input frequency of my input signal, the output frequency is the amplitude of the output signal is changing as well. And in this case, since the reactance is decreasing when I'm increasing the frequency, the output voltage is decreasing as well. and this equals a low pass characteristic. An important tool to visualize the characteristic of a filter is the so-called body diagram. The body diagram consists of a frequency and a phase response. The frequency response defines the output amplitude behavior of the filter. So it basically visualizes the output amplitude in relation to the frequency. The phase response basically defines the characteristic of the phase shift between the input and the output signal of the filter. In this example here, you see the body diagram of a first-order low-pass filter. The -3 dB point is indicated in red and is at 10 kHz. And if you have a look at the phase shift at the -3 dB point, so at 10 kHz, the phase shift is -45 degrees. So that means there is a phase shift of -45 degrees between the input and the output signal of this filter. Some important terms when we are talking about filters are frequency, period, phase delay, and phase. The frequency f is the repetition rate of a sine signal or other periodic waveform in cycles per second or hertz. So if we have a look onto the graph on the blue sine signal, we can clearly see that this blue sine signal repeats once per second. So that means the frequency of this signal is 1 Hz. The period t is the time in seconds that the sine signal or other periodic waveform repeats. Again, if we have a look into the graph, the blue sine signal, we can clearly see that the period of the sine signal is 1 second, since within 1 second it runs through one cycle. So how is the relation between the frequency and the period? Frequency is equal to 1 divided by the period. When we are talking about the phase delay, we are talking about the time difference between two periodic waveforms at the same frequency. So again, if we have a look into the graph on the right side, we can clearly see marked in green the phase delay between the blue sine signal and the red sine signal, which is 0.2 seconds in this case. However, if we are talking about the phase, we are talking about an angular difference between two periodic waveforms at the same frequency. So again, if we have a look into the graph on the right side, we can see the green marking, which basically indicates the phase. And in this case, the phase between the red and the blue signal is 72 degrees. And the reference is always one period, which equals 360 degrees. So when we are talking about phase delay and phase, we have to be aware that we always talking about the same difference, but one time we are specifying this difference in seconds, and when we are talking about phase, we are specifying this difference in degrees or radians. In this example, I'm going to show you for different frequency points in the body diagram how the filter reacts in the time domain. On the left side, you can see the body diagram of a first-order low-pass filter with a cutoff frequency of 10 kHz. We start with our comparison at the frequency point number 1, which is at the frequency of 1 kHz. So if we have a look onto the frequency response on the left side, we can clearly see that at 1 kHz the amplification is at 0 dB, which means we don't have any damping yet. When we have a look into the phase response, we can see that at 1 kHz there is already a slight phase shift of around -6 degrees. So now if we have a look on the right side into the time domain, we see the red signal, which is the input signal, and the blue signal, which is the output signal of the filter. And since we have an amplification of 0 dB, there is still no difference between the amplitudes. So the input signal and the output signal have still the same amplitude. However, there is already this slight phase shift of roughly -6 degrees. Now we are increasing the frequency to point number 2, which is at 10 kHz. Again, we have a look into the body diagram on the left side, and we can clearly see that at 10 kHz we are at the -3 dB point. So the amplification is -3 dB. If we have a look into the phase response, we see that at 10 kHz we have a phase shift of -45 degrees. So again, we see how the filter reacts in the time domain on the right side. There we can clearly see that the output signal, which is the blue signal, is already attenuated to roughly 71% of the input signal. And we can clearly see this phase shift of -45 degrees between the red input signal and the blue output signal. So now again we are increasing the frequency to point number 3, which is at 100 kHz. Now if we have a look into the frequency response on the left side, we can clearly see that at 100 kHz we have an amplification of -20 dB, and if we check the phase response, we can see that we have a phase shift of roughly -85 degrees. So how does that look in the time domain? Again, we can see that the amplitude of the blue output signal is now further reduced. It's at roughly 10%. So this 10% equals this amplification of -20 dB we can see in the body diagram. And we can clearly see that there is a phase shift of roughly -85 degrees between the red input signal and the blue output signal of the low-pass filter. When talking about filters, we have to be aware that we not only distinguish between different filter types like low-pass filter, high-pass filter, band-pass and band-stop filter, we also distinguish within the same filter type between different filter characteristics. The most important characteristics are the Butterworth, Bessel and Chebyshev characteristic. On the right side of this slide, you see the frequency response of different low-pass filter characteristics of the same order. So now we are going to compare the different filter characteristics. In the end, it really depends on the application requirements which characteristic is the most suitable. When we have a look at the Butterworth characteristics, the properties here are a maximum flat frequency response in the passband and a monotonous attenuation in stopband. You can clearly see this in the frequency response on the right. So the red curve, which is the Butterworth characteristic, is very flat in the passband. The advantage of the Butterworth characteristic are a good amplitude behavior in pass and stop band. However, the disadvantages are quite a low steepness in the transition zone. You can see this if you compare the Butterworth characteristic, which is the red characteristic, with the Chebyshev. The steepness is lower than the Chebyshev characteristic. If you're having a look at the Bessel characteristic, the properties here are mainly impulse forming. The advantage of this characteristic is a constant group delay in the passband. And the disadvantage, which you can clearly see in the frequency response graph, is a very low steepness in the transition zone. Last but not least, the Chebyshev characteristic. The properties here are a very wavy behavior in the passband. You can clearly see this if you have a look at the green characteristic. It is very wavy in the passband, and it has an attenuation in the stopband which is monotonous. The advantages of these characteristics are a good steepness in the transition zone. You can clearly see this. The Chebyshev characteristic, which is the green line, is the steepest characteristic of the three. However, the disadvantages of this characteristic are a big variation of group delay, which in the end leads to a bad time behavior. FFT filters are filters with a special characteristic I'm going to explain in this example. Important to know is that FFT filters can only be applied as post-processing filters in a post-processing software. In this example, we are going to apply an FFT filter on a 1 kHz rectangular signal, which you can see on the top of the slide as a blue signal. So we start with this rectangular signal in the time domain, and as a first step, we are going to transfer this time domain signal into the frequency domain by an FFT transformation. What we end up is with the frequency spectrum of this 1 kHz rectangular signal. So you can see the most dominant frequency, the fundamental frequency of the 1 kHz rectangular signal is the 1 kHz frequency, and then you see all these harmonics at 3 kHz, 5 kHz, 7 kHz, and so on. And now what we are going to do is we are going to apply a low pass 2 kHz FFT filter, which is indicated in red in the second graph. A special characteristic of this FFT filter is that it has a very high steepness. That means it really sharply cuts right at the cutoff frequency, in this case 2 kHz. So we can clearly see this if we have a look at the frequency spectrum after we have applied this FFT low pass filter of 2 kHz. You see this in the green frequency spectrum. Only the fundamental 1 kHz frequency is left, and all the upper harmonic frequencies from 3 kHz upwards are filtered, so they are gone. And now to go back to the time domain, what we do is we do an inverse FFT, so an inverse fast Fourier transformation to transfer the frequency domain back to the time domain. So this is the last graph. So now you see the result in the time domain. So there is only the fundamental sine wave signal with a frequency of 1 kHz left. So the takeaways here are FFT filters can only be applied as software post-processing filters, and they have a very high steepness, what we have shown in this example. So that means frequencies above the cutoff frequency are filtered. In this real-world example, I'm going to show you how filters can improve the signal quality. In this example, we see three force curves. Basically, The three force curves are of low frequency content, but superimposed onto these three force curves we see a very high frequency interference. So what are the options we have here to improve the signal quality? We can select a low-pass filter on the signal processing device, or we can use a digital low-pass filter in a post-processing software. The second option has the advantage that we do not lose the original data. So whenever we are not so sure what kind of filter we are going to set, maybe it's then a good idea to acquire the raw signal and then try different filtering options in a post-processing software. So how does the result look like once we have applied a low-pass filter onto these three force signals? Here is how this looks like. So you can clearly see that the superimposed high frequency interference has gone and is filtered. And you can clearly see the three force steps. What are the main learnings of this webinar? A filter always cuts away part of the measured signal. So it is crucial that you always carefully think about which frequency ranges you are interested in and which frequency ranges you want to get rid of. Maybe if you are not so sure about where to set your cutoff frequency, a great tool is always a software processing tools where you can play around with different filters options without losing your original data. Filters always cause a phase shift and time delay. This has to be taken into account if you have a measurement setup with multiple channels and you are applying different filters to these different channels. So then you have to be aware that this leads to different phase shifts among these signals. There is no perfect filter. Because of the roll-off characteristic of a filter, there is always some remaining signal content in the filtered range. Thank you for your attention.